Okay, let's just dive right into this explainer. We're going to set the stage for how we actually make sense of massive, almost incomprehensible amounts of data. And the secret? It's the incredibly elegant solution of sampling. I mean, have you ever really stopped to wonder how a survey of, say, just 1,000 people can accurately predict a whole national election? Or how a giant factory ensures the quality of literally millions of products without testing every single one? It kind of feels like magic, right? Well, spoiler alert, it's not magic at all. It's the strict mathematical discipline of sampling design. And today, we're going to break down exactly how this all works, turning what might seem like a really daunting statistical process into an intuitive, everyday toolkit.
So, here's our roadmap for today. We'll start with the power of sampling, clearly distinguish between the population and the sample, and then look at frames and sampling units. After that, we'll compare the two main sampling methods, navigate some common errors and distributions, and finally, wrap up with the hallmarks of a really good sample. Let's get into it.
Section 1. The power of sampling. Why we don't measure everyone.
All right, so we start with a pretty simple reality. It's literally impossible to pull an entire country or test every single item rolling off an assembly line. When you're doing research, it is almost never possible to study an entire population. You've got massive constraints, right? Time, money, complex logistics, the whole shebang. Which brings up a really major question. How on earth do we know what millions of people want without asking them all? Well, think about it like cooking. You don't need to drink the entire pot of soup to know if it needs a little more salt, do you? No way. A well-stirred spoonful does the trick perfectly. And that spoonful, that is your sample. That's the absolute power of sampling. It makes research feasible, it saves resources, and honestly, it forms the entire basis for inferential statistics. It lets us take what we learn from that one tiny spoonful and make incredibly smart policy or business decisions for the whole pot.
Section 2. Population versus the sample. Zooming in.
Think of this whole concept kind of like a set of Russian nesting dolls, filtering down from a huge theoretical group to the actual units we're studying. So picture the biggest, outermost layer. That is your target population, the complete set of individuals or items or events you eventually want to understand. But as we established, we can rarely access all of them, so we filter down one layer to the sampling frame, which is the accessible part of that target population. Finally, we drill all the way down into the center, the sample itself. The sample is just that specific subset of the population chosen for the study. And here's the crucial part. How well this tiny inner doll represents the giant outer doll completely determines how trustworthy your research results are going to be. Now, we need to draw a really clear line on how we mathematically describe these groups. Population characteristics, like the true average of everyone, are called parameters. Meanwhile, sample characteristics, like the average we actually measure from our smaller group, are called statistics. Actually, a really easy trick to remember this. Population has parameters, sample has statistics. The matching P and S starting letters make it super easy to lock in. And the entire goal of all this analysis, it's simply using our sample statistic to accurately estimate that true population parameter.
Section 3. Frames and sampling units. The blueprints.
Okay, to actually pull this off in the real world, you can't just walk outside and start randomly pointing at people, right? You need a structured plan. First up, we have the sampling frame. Think of this as your operational master list. It's kind of like an old-school telephone directory if you were doing a citywide survey. It is the exhaustive compilation encompassing all possible components within your population. But for your study to actually be credible, this frame needs a few specific things. It must be completely exhaustive, so no exclusions or duplications. It has to contain the latest info, because obviously, obsolete data is going to ruin your integrity. It must be highly accurate, and it needs the appropriate scope for whatever specific investigation you're running.
So, from that master list, we drill down to the sampling unit. The sampling unit is the absolute basic building block of your analysis. Identifying it is a step you literally must take before selecting your sample. Depending on your research, your unit could be an individual person, maybe a specific household, a geographical neighborhood, or even an entire organization. Simply put, it is the single entity from which you will extract your data.
Section 4. The two sampling methods, the playbook.
Once you have your blueprints, your frame, and your units, you basically have to choose between two statistical heavyweights. First, probability sampling. This guarantees an equal, random chance of selection to prevent bias. Think of it kind of like a lottery, where units are mechanically selected. This includes methods like simple random sampling, or dividing populations into geographical clusters, or even systematically picking, say, every 10th person on a list. Because it relies entirely on mathematical chance, we can precisely quantify any estimating errors. On the flip side, we have non-probability sampling. This is deliberate, and it's heavily based on convenience. It relies on personal opinion or researcher judgment rather than pure chance. Now, while this definitely introduces some personal bias and makes it pretty much impossible to quantify the error, it is still widely used. Why? Because it is incredibly fast and highly accessible.
Just to give you an idea of how these non-probability methods work in the real world, you've got a few different flavors. You have convenient sampling, literally just grabbing whoever is most easily accessible to you. Then there's purposive sampling, where you handpick subjects that meet very specific criteria. You also have quota sampling, making sure your sample matches specific demographic limits, kind of like filling in a pie chart. And then snowball sampling, which is super interesting. It's where initial subjects actually recruit future subjects right from their own networks. So yeah, while they don't have the statistical purity of a true random sample, they are absolutely fantastic and cost-effective for smaller studies, exploratory research, or when your time and money are just incredibly tight.
Section 5. Navigating errors and distributions, the pitfalls.
Now let's slow down for a second, because we have to acknowledge that sampling is not perfect. It has real-world stakes, errors are going to happen, and we need to know how to spot them. First up, sampling error. Even with the most careful selection process imaginable, there is always a natural margin of error. Why? Simply because we are studying a subset and not the entire universe. It's an inherent inaccuracy. It is the unavoidable difference between the sample statistic you measured and the true population parameter that actually exists out there. We literally can't avoid it. But if we use probability sampling, we can at least use statistical methods to estimate and manage it.
But we also face non-sampling errors. And these, things like measurement errors, processing mistakes, people just not responding, or interviewer bias, these are often way more troublesome. They can create deep, systemic biases right during data collection. And honestly, here is the kicker. Non-sampling errors are present in all surveys, even massive full-scale population censuses. Plus, there is currently no mathematical formula available to quantify non-sampling mistakes. You can only reduce them through really rigorous quality control, double-checking your data, and making sure your interviewers are trained properly. So, to manage all these uncertainties, statisticians rely on something called the sampling distribution. Imagine drawing hundreds or even thousands of random samples from your population and calculating the average for every single one. The overall pattern those averages create, that is the sampling distribution. And this leads us straight to the central limit theorem, which is an absolutely brilliant mathematical rule. It states that as your sample size gets large enough, this distribution of averages forms a beautiful, predictable bell curve, regardless of what the population's original shape looked like. This theorem is the actual magic that allows researchers to accurately predict entire populations using just a small subset. It's the core mathematical foundation that lets us assess if we're right and confidently apply what we've learned back to the whole pot of soup.
Section 6. Hallmarks of a good sample, the perfect polish.
All right, to wrap all this up, a truly reliable sample basically requires hitting 4 key markers. First, it must be highly representative, meaning it perfectly mirrors the diverse characteristics of the target population. Second, it must be adequately sized to shrink down that unavoidable sampling error we just talked about. Third, it should leverage randomness to prevent human bias from creeping in. And fourth, it absolutely must have independence, meaning picking one unit doesn't influence or dictate the selection of another. Hit these 4 markers, and your data is going to be rock solid.
Which brings us to our final takeaway. Understanding sampling isn't just a fun theory. It literally dictates the policies, the medical decisions, and the news we consume every single day. So the next time you see a flashy political poll on the news making some bold claim, ask yourself, what was their sampling frame? Did they actually use probability sampling? And ultimately, does that spoonful of soup really represent the whole pot? Keep asking those questions, stay curious, and thanks so much for joining me in this explainer.